Hi everybody, this is going to be our note for 5.5, first differences. So we're going to be able to calculate first differences using a table of values, and we're going to use first differences to identify if a relation is linear or nonlinear. So first differences are the differences between the consecutive y values in tables of values with evenly spaced x values. These parts are important to know. So consecutive y values means y values kind of going in order. So y value compared to the next y value compared to the next y value. And we can only compare these consecutive y values if the x values are evenly spaced, meaning the x values are going up by ones or by twos or by threes. So as long as the x values are going up by some constant amount. So if the first differences of a relation are constant, the relation is linear. And if the first differences of relation are not constant, then the relation is nonlinear. So what do you mean by linear and nonlinear? Well, hopefully the word that we see in linear is line. So if something is linear, remember when we graph it, it should make a straight line. And if something is nonlinear, well, that means like we can kind of derive from this no line. So we're going to have something on a graph that isn't a straight line. It might be like a curve. It might be something like this kind of curve, which you learned about in grade 10. It could be some different kind of shape altogether. So that is just not a straight line. So linear, straight line, non-linear, non-line, not a straight line. So let's get an example. It says, use first differences to determine which of these relations are linear and which are non-linear, and explain your reasoning. So again, how do we calculate these first differences? So first thing, when we have a table of values, we have to have a table of values for this. We have to make sure our x values are going up by the same amount. In this case, they're going up by ones, so we can use our first differences here. So now to use our first differences, all we have to do is get the lower value here and subtract it from the upper value. So we're going to do 3 minus 7 here. Now 3 minus 7, if we use our calculator, we're going to get negative 4. So I'll do this again, but with the lower y value, subtract the upper y value. So negative 1 minus 3. And if I subtract those two, I get negative 4. So again, the lower y value, subtract the upper y value. Negative 5 minus negative 1. And we're keeping our signs the way they are here. So negative 5, subtract this negative 1. This two negatives will make a positive. So negative 5 plus 1 will give me negative 4. And last time, negative 9, subtract negative 5, which will also give me negative 4. So these are our first differences because I'm really just counting the differences for the y values the first time. So this minus this, this minus this, this minus this. So all of these are the same. So we're going to say that this is a linear relation. So type of relation is it's linear. And the reason is because the first differences are constant, which just means the same. So because the first differences are the same here, if I were to graph this, I should get a straight line. All right, so this one is going to be the same thing. We have to make sure the x values are going up by a constant amount or the same amount. So this time they're going up by tens, which does work out. What I mean, like, are they going up by the same amount? Like if this was like 10, 12, and then 15, and then 16, and then 20, well, then we wouldn't be able to do the first differences here. We have to make sure they're all going up by the same amount for these x values. So because these are going up by 10, now I can use my first differences. I'm going to do the lower y value, subtract the upper y value. So 1 minus negative 1. That gives me 2. Then 5 minus 1. Again, the lower y value, subtract the upper y value here. We're going to get 4. So this one, subtract that one, I get 13 minus 5, which is 8. And then 29 minus 13, which is 16. So these first differences are not the same. They're not constant. So this relation is going to be non-linear. And why is it nonlinear? Well, the first differences are not constant because they're all different numbers here. So it is nonlinear because the first differences are not constant. All right, for part C, try this one on your own, and then you can kind of pause the video, and then when you're done, unpause the video, and we'll take it up together. Okay, same thing we do. We just check if the x values go up by the same amount. They're going up by 5s, so this works out. Then I'll just do my lower one, subtract the upper one here. 10 minus -5, which is 15. Then we have 25 minus 10, which is 15. 40 minus 25. You can already kind of start seeing it. And then 55 minus 40. Now, do we have to do it for all of these? You should, because what if we just did it for all of these, but the last one here was a different number? So just to be sure, we should do it for all of these. But if you're wondering, is that a lot of work? Well, we just had to do like 4 subtraction questions. So as long as you can do this, I don't think it should take too long. You can double check in your calculator as well. But the main thing is knowing that we subtract the lower one, subtract the upper one, and just keep going in that pattern. So we can say from this relation, it is going to be linear for the reasoning of, well, these first differences are constant. Again, or the same. So as long as these first differences are the same or constant, like they're always going to be 15, we'll have a linear relation, which means if I were to graph this, I would get a straight line. All right, example 2 says, complete a table of values for each equation given, then determine if the first differences are constant and state whether the relation is linear or nonlinear. So our equation here that they have is y is equal to -2x plus 7. So how can I figure out the y values here? Well, we're given some x values here. If we weren't given these, we could just choose some x values. But we are given 0, 1, 2, 3, and 4. So we're going to get our equation here. And remember, I can rewrite this because even though this is y equals -2x plus 7, I could also say that -2x plus 7 is equal to y. If you're like, well, how come we can do that? Well, it's like saying 2 times 3 is equal to 6, or 6 is equal to 2 times 3. These both mean the same thing, even though the equal signs are on either side. So I'm going to write our equation like this right now, except instead of putting x there, we're going to substitute the x with the x values given here. So what I'm going to do is I'm just going to first just write that equation out every time. I'm going to leave the x blank so I can replace it with the x value that we have there. Oops, that's not even close. I don't know how because I got the 4 there. So there we go. So I'm going to put in my values here, 0, 1, 2, 3, and 4. So if I follow my BEDMAS here, -2 times 0 is 0 plus 7 will give me 7. -2 times 1 is -2 plus 7 is going to be 5. -2 times 2 is going to be, well, I'll write this one out, -4 plus 7, which is 3. Fine, I'll write this. 0 plus 7 is equal to 7. This is -2 plus 7, which is equal to 5. -2 times 3 will give me -6 plus 7, which is equal to 1. And then we get -8 plus 7, which is -1. So these are my y values after inputting these x values. So now I can use my first differences. 5 minus 7 is equal to -2. 3 minus 5, -2. 1 minus 3, -2. And -1 minus 1 is also to -2. So the first differences are constant. Therefore, the relationship is linear. So let's do this with a noble partner, but again, we're not doing that currently. Mainly because you're watching this probably at home and you might not have somebody beside you who can do this with you. If you do, you can do that, but otherwise we can just watch the video. So we have y is equal to x squared here. So same thing, I'm just going to rewrite this so the y is on the other side, just so I can just, is equal to, I'll know it's going to equal y on this side. So I'm going to just write my equation again, but instead of x, I'm just going to leave a blank because the x values here they're going to change depending on the x values that they gave me. So this is going to be 0, 1, 2, 3, and 4. So 0 squared is 0. 1 to the power of 2, or 1 squared, is just 1. 2 squared is 4. 3 squared is 9. Again, we're not doing 3 times 2 here. It's 3 times 3. 4 squared is going to give me 16. And if I did my first differences here, 1 minus 0 is just 1. 4 minus 1 is 3. And we can already kind of tell, but we'll just do it for all of them. 5 is 7. So the first differences are not constant. Therefore, the relationship is non-linear. If you must know, this is actually something you're going to learn about in grade 10. I'm actually doing this right now with the grade 10s. So just a little kind of spoiler for what you're going to do next year. All right, so example 3 says, Jody works at a factory that produces square tiles for bathrooms and kitchens. She helps determine shipping costs by calculating the perimeter of each tile. So we're going to kind of be drawing these tiles just down here so we can actually describe them afterwards. So it says calculate the perimeter and record your answers in the perimeter column of the table, and describe what happens to the perimeter of each tile when the side length increases by 1 centimeter. So what this means is if I have a tile here, and we're saying the length and width is going to be 1 centimeter. So remember, these are square tiles, so all the side lengths are the same. So this is going to be 1, 1, 1, and 1. So to find the perimeter of anything, we just have to add the outside, or add all the lines here. So 1 plus 1 plus 1 plus 1 is going to give me 4. And they're saying, well, what if the side length is now 2? So it's a little bit bigger. Well, I guess those side lengths are double the length. So this is 2, this is 2, this is 2, this is 2, 2, 4, 6, 8. Get 8 there for the perimeter. Then we're doing it for 3. Again, not drawn to scale because this is probably a bit too big, but that's okay. 3, 3, 3, 3, 3, 6, 9, 12. Then we do it for 4. You can kind of get it 4 plus 4 plus 4 plus 4. That's 4 times 4, which is 16. And then 5 times 4 is going to be 20. So what is happening to the perimeter every time we increase the side length by 1 centimeter? Well, it looks like by looking at the perimeter here, it goes up by 4s. So we can say the perimeter goes up by 4 when the side length increases by 1. So we can see that happening here. Now it says construct a graph of the perimeter with respect to the side length. So which one depends on the other one now? Does the side length depend on the perimeter, or does the perimeter depend on the side length? Well, the perimeter depends on how long this is. Also, this is the first column in our table, which is usually our independent variable. So I'm going to draw a graph down here, and our side length will be on the x-axis because it's the independent variable. So we're going to go by, we'll just go by ones. 1, 2, 3, 4, 5. Sorry, this is going to be in centimeters. And then our y-axis will be perimeter in centimeters as well. That says perimeter. And it looks like we're going up by 4s here, so I could start at 0 and then go 4, 8, 12, 16, 20. We can go up a little bit more. Okay, we want to go up a little bit more sometimes in case we need to extrapolate, so find some more, extend our line to get some more data. So I'm going to go 1, 4, 2, 8, 3, 12, 4, 16, and 520. So just a reminder, I didn't just plot these points here on the y-axis and then these ones on the x-axis. These only work out because these are going up by the same scale. So because this is going up by 4s, I'm able to do this. This goes up by 1s, so I'm able to do this. If these were going up by different amounts, then I'd have to choose a better scale where all the numbers are going up by the same amount every time. So please just don't think I just have to copy these as the y values here and these as the x values. It just happens to work out in this case for that. So I'm going to do this, join these together, trying to make it straight. There we go. So use the graph to describe the relationship between the perimeter and the side length. So what's kind of happening here? It seems like every time our side length goes up by 1, our perimeter goes up by, so we can say as the side length goes up by some number, the perimeter goes up by something else. So as our side length goes up by 1, our perimeter goes up by 4. Because again, our perimeter is going up by 4 every time. Describe the shape of the graph. Well, we can say this is a positive graph, a positive line, and also it is linear because it makes a straight line. So now calculate the first differences by adding the first differences column in table in part A. What did you notice about the first differences? So let's calculate the first differences here. I'm going to have the lower one subtract the upper one. So 8 minus 4 is 4. 12 minus 8, 4. 16 minus 12 is equal to 4. And 20 minus 16 is equal to 4. So these are our first differences. They are constant. So we can say that first differences are constant. So we know it's going to be linear. And therefore linear. We can confirm it's linear because we also graph this and I made a straight line as well. Sorry, I just read this and I can understand how it's a bit confusing. Is we're not adding the first differences here. They just want us to add a first differences column where we just kind of calculate the first differences. But we've already been doing that. I don't really draw this extra part of the table. We can if we wanted to. It might be a little bit more proper, but I just kind of do the calculation there. So we did the first differences in this extra column, and we found that they're constant. So this is a linear relation. So summary, the plotted points suggest a linear relation, and the first differences are constant. All right, let's go to the next example. All right, so now we're going to do this again, except we're going to be doing it for the area of a tile. So if I had to, so it says Raj, another employee at the factory, also works with side lengths of each tile. Calculate the area and record your answers in the area column, and then describe what happens to the area of each tile when the side length increases by 1 centimeter. So I'm going to do this again. I'm just going to do it for side length of 1 and 1 here. So if I'm finding the area, 1, because area of any square or rectangle is length times width. So 1 times 1 is 1. Then if this was side length and width of 2 by 2, because again it's a square tile, 2 times 2 is 4. Then we'll do it for 3. And we get the picture here. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. Then we can construct a graph of this. So we're going to have side lengths, because again, which one depends on the other? Well, the area depends on how long these sides are, because we can't calculate the area unless we know these side lengths. So this depends on this. This is also the first column, so usually it's the independent variable. So we're going to put side lengths here again. And our units are important, so we're going to put centimeters, and then the area is centimeters squared. So I'm just going to go up by ones here. 1, 2, 3, 4, 5. And then, well, now we're not going up by the same number this time. So I can't just put these numbers here now. I have to go up by by a scale. So if I went up by ones, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, that doesn't account for these last 2 points. So going up by ones doesn't really work. What if I went up by twos? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That also doesn't incorporate the last one. So going up by twos won't work either. What if I went up by like tens? 10, 20, 30, 40. Okay, that's way too big of a scale. So what if I went by threes? 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. That's not too bad. So we'll go up by, what if I went by fours? 4, 8, 12, 16, 20, 24, 28. Let's go up by fours. Threes was fine, but I'm choosing fours. 20, 24, 28. Again, because if I wanted to just extend the graph a little bit, we have some extrapolation going. I would want to maybe go by 4, so I have a bit more space up here to extend my graph if I need to. So at 1, we have 1. So I know that's harder to graph here. So if this whole square, I'll zoom in here a little bit, or a lot maybe. If this whole square from here to here is 4, then I can kind of divide this square up into 1, 2, 3, 4. So I can say x is kind of 1, 1 is going to be here. And then 2, 4, well, 2, 4 will be here. And then 3, 9. Well, 9 is just a little bit more than 8. And then 4, 16. And then 5 and 25. And 25 will just be a little bit more than 24. So we can see here, we are going to be starting at 0, 0 as well. So we're going to join this, and we're going to get this kind of curve going on. So now zooming out to answer this question. Use a graph to describe the relationship between area and side length of a tile. So we can say as the side length increases by 1, we can say the area goes up by, and there's no pattern like we had with our first differences here, like if we're going to calculate the first differences, but there's no like going up by the same amount here. So what's really happening in the area, it's really just our side length to the power of 2. So we can see the area goes up by the side length squared. Just to make this sound a bit better, we're not going to say the area goes up by the side length squared, it's more the area and say changes to the side length square. Changes to. So whatever the area or the side length increases by 1. The new area is changed to whatever that new side length is squared. We can describe the shape of this graph. Is it a straight line? Then we can say it's a curve. You could also say it's non-linear because it does not form a straight line. Then if we're to calculate the first differences here, 4 minus 1, 9 minus 4, 16 minus 9, 25 minus 16, we'll get 3, 5, 7, and 9. So these are not constant. So we can say, what do you notice about the first differences? They are not constant. And the plot points suggest a nonlinear relation. And the first differences are not constant. So I think we start to get the idea here of how we can check if something's going to be linear or nonlinear. As long as we have a table of values, or if anything, as long as we have the equation and some x values, we can determine whether a relation will be linear or nonlinear based on those changing y values. So we're going to do this a couple more times. So here we have deep sea divers. The table below shows some data collected as divers descend below sea level. Calculate the first differences, then use your first differences to determine if the relationship is linear or nonlinear. Then you can check our graph afterwards. But we can graph these points and see if it's going to be linear or not. So try this all on your own, I'd say, and then when you've figured it out or have your answer ready, then unpause the video and check it with mine. So just doing first differences, we're going to have -4 minus -2, -6 minus -4. And again, if you're wondering, well, how is it -2 minus -4? Well, it's always this subtract this, and the signs belong to the numbers in front of it. So or the signs belong to the number that's next to it here. So this is -4, subtract, and this is -2. So we just have to subtract some integers here. -8 minus -6, -10 minus -8. So we can just type this in our calculator. We should remember that the two negatives make a positive. So -4 plus 2 is -2. -6 plus 4, also -2. And we should kind of see that these are all going to be -2 here. So when we graph this, this should be a straight line. So here our graph looks a little bit different. We're actually using a different quadrant in our Cartesian plane. The horizontal is still the x values, and the y values are still the vertical ones. So we're going to have time on the independent variable, 0. We'll do every other line as maybe 1, 2, 3, 4. Also, I should put my units, which is in minutes. Here we're doing depth in meters. So I'll go by an appropriate value for our y values here. Well, they're going up by, it seems like -2, so we'll actually go by -2, 2, -4, -6, -8, and -10. I'll plot these points, 0, -2, 1, -4, 2, -6, 3, -8, and 4, -10. And all these points will make a straight line. So I can ask you, is this going to be direct or partial variation? We said for direct variation, the line always passes through the origin, and this one does not. So this has to be partial variation. But we have at least confirmed that our first differences are constant, and we have a linear line, or linear graph anyway. Hot air ballooning. So this is our last one. The table shows the data collected as a hot air balloon leaves the ground. Calculate the first differences, then use the first differences to determine if the relationship is linear or nonlinear. So yes, we've done this a bunch of times now, so hopefully we have a better understanding of it. But we'll just do it one more time, because you know what? We're already here. You're already watching this video. At this point, I'm not sure how long it is. How long are we talking about here? Yeah, we're at like almost the 30-minute mark here, so we might as well just finish this up. 4 minus 2 is 2, 2, 2, and 2. So now we're going to graph this again. Now our height is kind of going upwards. I mean, in this graph, we're doing depth, so it kind of made sense we could do it this way. But now this hot air balloon is going upwards. So we're going to have the height in meters, because this is our dependent variable because we have time here. And we always said time is the independent variable in seconds. So this is going up by ones. We'll do the same thing. 1, 2, 3, 4. Then we'll do it for our y values for the height. We'll go up by, again, 2, 4, 6, 8, 10. And these are all the same. It should be a straight line. We have 0, 2. Also partial variation now because it's not starting at 0, 0. 1, 4, 2, 6, 3, 8, and 4, 10. So then we just see that once we join these, we have a straight line as well. So that is it for 5.5, which is first differences. We only have one more section of chapter 5 left. So please try the homework, and thank you for your time.